Okay, students. So I hope all of you are doing well. Let's get started today with May June 2024 paper 4 variant 1. Okay. So let's get started. This is your ATP ka paper. A student finds the volume of a small glass ball marble by two different methods. Okay, there are two different methods to find the volume of a glass ball or marble. Okay, let's see the method 1. The student places 6 small balls by the side of a meter rule as shown in figure 1.1. Okay, make sure that there are no gaps between the balls. Okay, we can see this diagram figure 1.1. The student has placed 6 balls side by side and there are no gaps in between them. Okay, take readings on the meter rules of the positions of point A and B as shown in figure 1.1. Let's take the reading of position A. This is 10, this is 10.1, this is 10.2. A is 10.2 centimeter. Okay, let's see point B. This is 19.5, this is 19.6, this is 19.7. B will be 19.7 centimeter. So your position at A will be 10.2 centimeter. Your position at B will be 19.2 centimeter. Simple as that. Let's further move ahead. The length L on figure 1.1 is the distance between point A and B. Okay. The average diameter of one ball can be found using this equation. Okay. Use your answer calculated in A1, that is this. Okay, this wala answer. To calculate the length and diameter, give your answer to the nearest 0.1 centimeter. Okay, let's first of all calculate this length L. How will we calculate this length L? Very easy. We will subtract the distance at point B from the distance at point A. This will, okay, this is 19.7, sorry. This is 19.7 minus 10.2. This gives you an answer of, let me put this in the calculator. 19.7 minus 10.2, this gives you an answer of 9.5. So your length is 9.5 centimeters. Okay, so let's write it here. Your length is 9.5. Let's calculate D as well. L is equals to 6D. 9.5 divided by 6 is equals to your D. What will be equal to your D? D comes out to be 1.6 centimeters. Okay, let's further move ahead. The average volume of one glass ball using this method is given by this equation. Okay, your volume is equals to 3.14 divided by 6 D cube. Okay, so let's calculate V. 3.14, D is 1.6. whole cube divided by 6. So this comes out to be, let me put this in the calculator, 3.14 divided by 6. This gives you an answer of volume as 2.1 cm cube. Simple as that. Let's move on to part B. In part B, we are applying method 2. Let's see what is method 2. The student pours water into a measuring cylinder. Okay. The volume of water in the measuring cylinder V1 is shown in figure 1.2. Let's see what is this initial volume. This is 25, this is 26, this is 27. So the initial volume in the measuring cylinder is what? 27 cm cube. Okay, let's further move ahead. The 6 glass balls are carefully added to the water, okay, in the measuring cylinder. The new reading on the measuring cylinder V2 is shown in figure 1.3. Okay, let's zoom in and see this reading. This is 39. Okay, this is 39. The volume Vt of the 6 balls is given by this formula, where Vt is V2 minus V1. Okay, our V2 was what? V2 was 39. What was V1? 27. Subtract both of them. You will get an answer of 12 cm cube. Let's place it here. Okay, calculate the average volume of one ball. We have to calculate the average value of one ball. Okay, let's do that. This is the volume for 6 balls. So divide this by 6. If 12 centimeter cube is the volume of how many balls? 6 balls. What will be the volume of one ball? Let's put a x here. Let's say this is one ball. Cross multiply it. Your x or the volume for one ball will come out to be what? 12 divided by 6. That is 2 centimeter cube. Now there is a catch here. You have to give your answer nearest till 0.1 cm cube. Since we have no decimals here, what will we do? We will place 0.0 here to meet the requirements of the answer. Okay, let's further move ahead. Suggest whether method 1 or method 2 gives the more accurate value for the volume of the ball. Which method 1 or method 2 is more accurate to calculate the volume of the ball? According to the answers, in method 2 you were getting an answer of 2 cm cube. And in method 1, if you see, your answer of volume was coming out to be what? 2.1 cm cube. Method 1 seems to be more accurate. Why? Because in method 1, you can measure up till what? Up till 0.1 cm cube. Do you understand this? In method 2, you didn't have the option of knowing the number after the decimal place. That is 0.1 cm cube. You can't measure it till 0.1 cm cube in method 2. However, in method 1, you can measure it till an accuracy of 0.1 cm cube. You will write here that method 1 is more accurate. And what is the reason? Because in method 1, we can measure the volume up to an accuracy of what? Up to an accuracy of 0.1 cm cube. Simple as that. Let's move on to the last part. The student now uses 6 glass balls to find the average mass of one glass ball using a small beaker and a top pan balance, electronic balance. Describe the method the student uses. Okay, a 2-marker question. What will be your step 1? Step 1 will be to measure the mass of empty beaker on electronic balance. What will be your step 2? What will be your step 2? In step 2, you will place the balls inside the beaker and measure the mass on the electronic balance and measure the mass on the electronic balance Let's label the mass obtained in step 1 as m1 and let's label the mass obtained in step 2 as m2. What will be your step 3? What will be your step 3? Calculate the difference in mass and divide it by 6 Simple as that. Let's further move to the second question. A student investigates how the temperature of the surrounding affects the rate of cooling of water. Okay. The student pours 100 cm cube of hot water into 250 cm cube of a beaker. Okay. He uses a thermometer to take the temperature of the water at time t is equals to 0 seconds. Okay. The thermometer reading at time t is equals to 0 seconds is shown in figure 2.1. Okay. Let's see what is the thermometer reading here. always remember that we use the lower meniscus to take the reading. This comes out to be what? 72 degrees. Okay. Record the temperature of the water at T is equals to 0 seconds. That is what? 72 degrees centigrade. Let's zoom out and continue this question. The student then records the temperature theta of the water every 30 seconds for 240 seconds. The results recorded in table 2.1. Okay. Before taking each temperature reading, the student carefully stirs the water in the beaker. Explain why. Why does the student stir the water in the beaker before taking each reading? Why is the case? Because, or you can rephrase it like this, that stirring up the beaker enables even spread of heat throughout the liquid. Okay, let's move on to part I3. Calculate the average cooling rate C1 of the water for the first 90 seconds of the experiment. Use the readings in table 2.1 and the equation this. Okay, we have to use this equation and have to calculate C1. So what was the temperature at 0 degree centigrade? 72. Okay, let's highlight this. What was the temperature at 90 degrees? 66. Okay, we have both the temperatures and the time was 90 seconds. Okay. So C1 is 72 minus 66 divided by 90. Let's calculate this. 6 divided by 90. This comes out to be 0.067. This comes out to be 0.067. What will be the units here? Temperatures have a unit of degree centigrade, and time, if we take it towards the top side, will have a units of second, or you can put a slash here, degree centigrade slash, and the answer is 0.067. Calculate the average cooling rate C2 of the water for the final 90 seconds of the experiment. Okay. So let's see what is the temperature at 150, 64, and at 240 the temperature is 61. Okay, subtract both of them. 64 minus 61 divided by T, that is 90. Your C2 will come out to be 3 divided by 90. This equals to 0.003 degrees centigrade per second. Compare your values of C1 and C2. Explain any differences in these values. As you can see, it is obvious that C1 is greater than C2. Okay, so first of all, let's write that C1 is greater than C2. Why is this the case? Why is C1 greater than C2? Because as you approach room temperature, as you can see, we are approaching room temperature. As we are increasing in time, what is happening? Your temperature is slowly approaching the room temperature. As you are approaching the room temperature, there will be a lesser drop in the temperature of the beaker. So you can write it here, because as you approach room temperature, the drop in temperature is less. The student repeats the procedure in A part 1, but this time he places 250 cm cube beaker inside a larger beaker containing iced water. Okay. This arrangement is shown in figure 2.2. Okay. The student reads the temperature theta of hot water, records the reading and immediately starts the stopwatch. Okay. Table 2.2 shows the temperature theta at 0 seconds, 30 seconds and 90 seconds. We have to calculate C3. Let's calculate C3. C3 is 75 minus 57 divided by temperature, that is 90. Let's calculate this answer. 75 minus 57 divided by 90. This comes out to be 0.2. What will be the units? Again, degree centigrade / seconds. Okay. Describe how C3 differs from C1. Explain your answer. We can say C3 is greater than C1. Why is this the case? Why is C3 greater than C1? Because as you can see here, beta, yahan pe, here in the case of C3, you have ice here that provides a greater amount of cooling. In C1 and C2, there was no ice. There was no ice. So you will write here that ice provides a greater cooling effect. A greater cooling effect in case of C1. In case of C3, sorry. In case of C3. Let's further move ahead. The recorded readings show that this experiment is not a valid comparison of C1 and C3. By referring to the results recording in table 2.1 and 2.2, explain why this is not a valid comparison. Let's see the results, what is actually happening here. In table 2.2, you are starting with an initial temperature of 75. In table 2.1, if you go here, you are starting with an initial temperature of 72. So the initial temperatures are not constant, or you can say initial temperatures are not same. Hence the comparison is not valid. You can write it down here. The initial temperatures are not constant, or you can say same. Hence, this is not a valid comparison. Hence, this is not a valid comparison. Simple as that. Let's further move ahead. State one variable that should be kept constant to make a valid comparison. This should be an other variable other than the initial temperatures. You can say that volume of the liquid. Volume of the liquid that you pour, that is to be cooled down. Basically, the volume that is cooling down in temperature must be constant. Okay, let's further move ahead. A student measures the focal length of a lens. Okay, figure 3.1 shows the apparatus she uses and the position of the lens when a clearly focused image is formed on the screen. Okay. The student places the screen at a distance of d is equals to 60 centimeter. Okay, so this d is basically what? 60 centimeter. Okay. From the illuminated object, place the lens between the object and the screen so that the lens is very close to the illuminated object. Move the lens slowly away from the illuminated object until a clearly focused image is formed on the screen. Okay, pretty basic. Measure and record the distance x. Now you will have to measure this with a meter rule. I don't have a meter rule right now, so let's say this is coming out to be 2 centimeter. I am writing it here as an imaginary number. This is not the actual marking scheme. I am just writing it as an imaginary number. You can measure it with a meter rule. Let's say this is coming out to be 2 centimeter. Figure 3.1 is drawn to a scale of 1/5. Okay. Use your answer in part A1 to calculate the actual distance u of the object from the lens. Okay. If this is coming out to be 2 centimeter, in actual real life, this will be 5 times greater because the diagram is 1/5 times actual life. So 2 into 5, this comes out to be 10 centimeter. Let's place 10 here. Reduce the image distance v, the distance from the lens to the screen when a clear image is seen. Okay, we have to again calculate this distance y. Let's say this comes out to be 4 centimeter, and since it is 5 times 4 multiplied by 5, this comes out to be, let's say, 20 centimeter. Okay. Figure 3.2 shows the shape of the illuminated object, and figure 3.3 shows the image seen on the screen. Okay, this is the object and this is the image. What are the two properties of the image that you can see? First of all, it is laterally inverted. It is laterally inverted, and one more thing that you can see in the image, it is magnified. It is magnified. Let's further move ahead. The student moves the screen away from the illuminated object and repeats the procedure for d is equals to 70, 80, 90 and 100. Okay. Table 3.1 shows the values recorded. Add your values for u and v from a part 2 and a part 3 to table 3.1 on figure 12 on page 12. Complete table 3.1 by calculating values of u into x for each value of d. Okay, so now I took assumptions here. Let's say it will be 2, then it will become 10, and I took every assumption here for u and v. But since we have to draw a graph, I will just cheat and take my values from marking scheme, because currently I don't have a meter rule at my disposal. U की value from the marking scheme is 24 and v is 36. Okay. So let's also fill this table out. U into v, this is 864. Also, one more thing that we must keep in mind is that we have to answer till 3 significant figures. Okay, so keep this in mind. Let's multiply 21 into 49. This comes out to be 1029. 1029. Now these are 3 significant figures. Let's convert it into these are 4 significant figures. Let's convert it into 3. 1030. 19.5 into 60.5. This comes out to be 1179.75. Now these are 6 significant figures. We only need 3 significant figures. So this will become 180. 1180. 18.6 into 71.4. This becomes what? 13. This becomes 1328.04. According to 3 significant figures, this will become 1330. 1330. Multiply these two values as well. 17.8 multiplied by 82.2. This comes out to be 1463. This comes out to be 1463, which till 3 significant figures will be 1460. Okay. Use the grid provided in figure 3.4 on page 13 to plot a graph of u times x on the y-axis against d/centimeters on the x-axis. You do not need to start your axis from the origin. Draw the straight line of best fit. Okay. So on the y-axis, we have to plot these values. And on the x-axis, we have to plot these values. Okay. Okay. So we have to basically plot d on the x-axis and u into v on the y-axis. Okay. So first of all, the first step that you must do is to see what are the maximum and minimum values. The maximum value that you want to plot on the x-axis is 100. The minimum value that you need to plot on the x-axis is 60. This will allow you to develop the scale for the x-axis. I have already done that, but how have I done that? Let me explain to you. How many boxes do I have on the x-axis? 1, 2, 3, 4, 5, 6, 7, 8. 8 large boxes on the x-axis. What was my maximum value? 100 minus my minimum value, that is 60, divided by the number of large boxes. 40 divided by 8, that means one box, one large box on the x-axis represents what? 5 units. Let's do the same thing for the y-axis. On the y-axis, you have a minimum value of 864 and a maximum value of 1460. Okay, so let's do the same thing again. On the y-axis, you have 12 large boxes. So let's do it here. What was the maximum value? 1260 minus 864 divided by 12 large boxes. Your answer comes out to be 49.99. So that means on y-axis, one large box represents how many units? 50 units or 49.9 units. So this is how you will plot the scale. You have given the labels as well. You can see U into X slash centimeter square. On the x-axis, we have D slash centimeter. I have plotted the scale accordingly. I haven't started from 0, 0. I have started from 860 and 60. Why? Because the examiner has instructed me as well. And secondly, I want to take such a scale that covers most of my graph. Okay. Then I drew a line of best fit, and this is my line of best fit. Simple as that. Okay, let's see the part 3. The focal length f of the lens is numerically calculated as the gradient of the line. Okay, we are told that focal length is the gradient of the line. So I took 2 points on this line. One is this point, 80 and 1340, and the second point is 72.5 slash 1060. I took 2 points on the line and took the gradient. The gradient comes out to be 16. While taking points for the gradient, make sure they are far away on the graph. At least 50% of the graph should be between the 2 points. Secondly, you must draw a dotted triangle like this. And thirdly, you must label the points on the graph like this. I have calculated the gradient. Let's put it here, 16. Then let's see what is the last part. In the part D, the lens manufacturer states that the focal length of the lens is 15 plus minus 10%. Decide with a calculation whether your focal length agrees with the statement that shows your answer. Calculation must also be provided. So if the manufacturer is stating that your focal length will be 15 plus minus 10%, this means what? Your focal length can be at a highest value of what? 15 minus 15 into 10 divided by 100, that is 10% of 15, and the highest value of focal length can be 15 plus 15 into 10 divided by 100. The lowest value of f will be 13.5 and the highest value of focal length can be 16.5. So my focal length answer, that is 16, lies within this range. If I want to write it mathematically, 13.5 and 16.5 is my range for my focal length. Does my focal length that I calculated in the earlier part is in this range? Yes. So I will agree with this answer. Let's move on to question 4. I have already drawn this graph, so you can take a screenshot here if you want to. Yeah, this is the complete graph. And let's move further to question 4. In question 4, we have to plan an experiment to investigate how the thickness of metal wire affects its resistance. The resistance of a wire can be calculated using this equation. What is that equation? Resistance is equals to voltage divided by current. Okay. The following apparatus is available. 6 lengths of metal wires are given, an ammeter is given, a voltmeter, a power supply, several connecting leads and micrometer are given. So the experiment is pretty simple. What we will do is, we will take all these 6 connecting wires. We have 6 lengths of metal wires basically. We will take all these 6 metal wires and place it in the circuit like this. We will take the voltage key reading across this metal wire using a voltmeter, and we will take the current key reading across this metal wire using a ammeter, and there is a power supply connected in series with this metal wire. Okay. And how will we measure the diameter of this metal wire? We will measure the diameter of this metal wire using a micrometer. I have written the entire setup here. Measure the diameter of each metal wire using a micrometer. Okay, this will get you 1 marks. Then what do you have to do? Then you have to measure the voltmeter readings and ammeter readings. Calculate resistance using this formula. Voltage divided by current is equals to your resistance. Now you will repeat this experiment for all the 6 wires and plot this table. In this first column, you will write the number of wires 1, 2, 3, 4 and 5. In the second column, you will write the diameter readings that you will obtain from the micrometer. And in the third and fourth column, you will write the readings obtained from the voltmeter and ammeter. The fifth column will be calculated using which two values? Voltage and current. Resistance here will be calculated by voltage divided by current. Simple as that. Now let's move ahead. During this entire experiment, you have to make sure that the length of each wire is same. Why? Because resistance is affected by length. Resistance is directly proportional to length. If you vary the length, the resistance of the wires will vary. Secondly, your wires must be of the same material. All the 6 wires must either be of copper, lead, silver, whatever the material is, but the material for each wire must be same. Last but not the least, what should you do? You should plot a graph with diameter on the x-axis and resistance on the y-axis to see how both of them are related. Now, a curious question here might be, sir, why did you plot a diameter on the x-axis and resistance on the y-axis? Because diameter is an independent variable. What are independent variables? Independent variables are those variables which you vary. Independent variables are those variables which you vary in the experiment, which you can vary. Can you vary the diameter? Yes. What is your resistance? Resistance is your dependent variable. Resistance is your dependent variable. What are dependent variables? Dependent variables are those variables in an experiment which vary due to the independent variable. See, independent variables are those variables which you vary. What are dependent variables? Dependent variables are those variables which change due to the changing of the independent variables. And always remember, dependent variables come on the y-axis and independent variables come on the x-axis. Let me explain it again if it wasn't clear at the first time. Independent variables are those variables which you vary in an experiment. In this experiment, you are varying the diameter. So, diameter is your independent variable. It will come on the x-axis. Independent variables always come on the x-axis. Resistance, on the other hand, is a dependent variable. Dependent variables are those variables which change due to the changing of the independent variable. And dependent variables are always plotted on the y-axis. So this marks the end of the ATP paper. I hope you liked the video.